about Synapse Analytics and how to do exploratory data analysis using Synapse without investing too much in the creating the environments and building the environment. So you can do it basically from scratch. And this will be the idea for this meeting. And at the end, I would like you to see that this is something that everyone can start with. You do not have to be a data scientist. You just need to have a basic knowledge of SQL. You have to know how to write a basic select statement, and that's all. And you need to have data. This is what you need. So my name is Damian. Let me introduce myself very quickly. I promise this will be a better picture here now. So my name is Damian. I come from Poland. I am a Microsoft MVP since 2009, so quite a long time. Also, I'm doing a lot of trainings and work for company UVIC. In Poland, we have our data community, a very big data community, and we organize a lot of conferences, and one of those is one of the biggest one in Europe is so-called SQL Day. So the next SQL Day is in May. It will be partially hybrid, so if for people who cannot attend in person, you can always join online. Yeah, that's all about me, and I would like to tell you about the history when Synapse started and what problems it tried to solve. So basically, when we think about Synapse, we know that previously it was called Azure Data Warehouse. So as a data warehouse, we know that data warehouse is something when you have everything prepared and designed very carefully, and every table has a defined shape. If you look inside a table, you have a set of columns. Each column has its place, has its meaning. So to create a data warehouse is basically a very long-term job, but it's also very boring. So if you think about data warehouse, usually it takes 6, maybe 9 months, sometimes longer to build it. And requires, from my perspective, a lot of paperwork, because you have to prepare a good documentation to understand why we have tables there, what each table is all about, and what is the purpose of each of those tables. So on this slide, you see I have visualized the tables as a bottle of bottles of water. So you can imagine that if you would like to bring another bottle here, it's a very simple task. But you see, take a look how beautifully the bottle of waters are placed on this on those shelves. Everything is in its position. You know why the bottle is there. But you can imagine how much work it requires to keep this beautiful, to keep those shelves tidy and without mess. It's a lot of work. There is, however, several problems with, let's say, classical or classic data warehouses. Because, when you build something like this, you have to think about so-called storage, so how much data you can put into this, and of course CPU. CPU means that you have to pay for the processing power. Also, when you build a warehouse like this, it's not easy to extend the data warehouse, because you have to think about that your data warehouse will always grow. You will never shrink the data, because you have to keep historical data as well. So in one data warehouse, you have to keep data that are hot. So you have to think that for example, I do a lot of reporting, let's say for the current month or maybe current year, but then I have a lot of data from previous year, which I call warm, because I can do also a lot of reporting, like referencing reporting. And I have a lot of data that I can call them cold. So those are data, for example, 5 years old, which are accessed very infrequently, but I need to keep them. I need to keep the data because for different reasons. Because, for example, the data warehouse has to have all the history. So it becomes a very costly solution. It looks like this. Most of the time you build on premises, you have to have a lot of compute power and a lot of storage. So extending this means that instead of buying one hardware, you have to invest immediately in, let's say, another set of hardware and maybe even more. So it's a very costly solution. But the situation is even worse because, you know, what I was trying to explain is that the very ideal world. So I still think that having this, let's say, data solution, you can have it. But from the perspective of real life, it is almost right now, it is almost impossible that you will be able to create a data warehouse in that way in the first place. At some point, you might be able to build a data warehouse like this. But imagine a situation that you have data and you would like to just take a look into the data and perform some kind of analytics to have quick answers. Let's imagine that business people ask questions. So you don't want to tell them, hey, I need to build a data warehouse like this. Let's get back to your questions in 9 months. Because business does not work that way nowadays. You have to have the answers almost immediately. The other thing is that we have a lot of data from different data sources, not only relational. Most of the time now, the data is non-relational. So you have a bunch of files. The files can have a structure which is changing very frequently. So most of the time, we do not think about data warehouse, but we think about something like this, which is a data lake. So the data lake can be, it's a storage. Technically, it's infinite. So there are no technical limitations how big the data lake can be. And you can put anything to this data lake in the native format, because the data lake does not have any assumptions about the data format. You can put big files, you can put tons of files that are smaller in size, whatever you wish. You just need to put the data in it. So, but now there is a problem. Imagine that you have to build a data lake, which is kind of simple thing. So you build the data lake, and you have your data there. Some of those files are very useful, and you would like to analyze them very quickly. So imagine that the idea is that the useful data you would like to analyze now, the data is in all the green bottles. So how would you like to analyze data from this data lake? The task is that you need to take all the green bottles and analyze the data. How would you like to do this? And the answer is very simple. You need to do it very quickly because you don't want to swim in this data lake too long because there are too many other data. So how to do this? And the answer is simple. Use the fastest language possible. The fastest language possible is called SQL. SQL is the fastest language for data analytics. Also for data analytics on demand. And the data analytics on demand is something that I would like to present to you today. So Synapse is the central part of the modern data warehouse architecture, as you see. So you see Synapse is somewhere on the right-hand side in the top. On the left-hand side, we have the data sources, which can be literally anything. So there are also no limitation what the files are, what is the data source, could be literally anything. Then most of the time, this is only a referencing architecture. This does not mean that it has to be always this way, but at least you know what you should have. So if you would like to get the data from the data sources, most of the time you have to have some kind of engine that can take the data from the data sources and put to the data lake that I have mentioned. So most of the time you would like to use Azure Data Factory as the orchestrating engine for this purpose. But I can also imagine that it can be like a Azure Function or Event Hub or Stream Analytics or whatever service that can take data from one place and put the data to another place. In this Azure, if we think about Data Factory, you can also imagine that you can perform some kind of transformation while moving the data from source to the Azure Data Lake storage. This is not always mandatory because let's say the pattern is not like extract, transform, and load, but it's a little bit different. It's like an extract, load, and transform, which means that transformation is not done in the Data Factory, but it's also possible. So what we can do if we have already data in data lake storage. So most of the time we think about big data volume at least. So you have a lot of data there. What you can do, you can build your machine learning models or perform very advanced, let's say, data transformation using Databricks cluster, because you can then use, for example, Python or Spark languages or SQL, Spark SQL, to perform this type of analytics. But the same thing you can also do in Synapse. And this type of analytics I'm going to show you in a moment. So once we have this analytics done, then you can do reporting, or you can build analytical model depending of the needs. So this is the architecture that as of now exists in the cloud, and I think we should follow it as much as we can. So what is Synapse actually? So Synapse is, previously it was Azure Data Warehouse. So we have thought about Synapse like a data warehouse, which is in the cloud. So you still have a bunch of tables. You can create views, store procedures, databases, like something like this. So this is still exists, and you can build this type of structure. So let's say regular data warehouse on so-called dedicated SQL pool. So this is what does it mean? This means that you have a predictable performance because each of the dedicated pool, it has a number of so-called data warehouse units. And those data warehouse units are like a processing power. So the more you pay, the more power you have. And of course, you can also scale it up and scale it down. Unfortunately, this is not done yet, let's say, in automated way. So you have to perform those tasks by yourself. But then there is a new kind of pool has been designed by Microsoft team. They design serverless SQL pool, which means that this is some so-called on-demand. So the pool is always available for you. However, you cannot control how much power is inside the pool, but you can do on-demand tasks without investing too much into the let's say, building a data warehouse. So this will be a perfect solution for exploratory data analytics, which is a topic for today. And it's also very important because you are only paying for the number of terabytes you have processed. So it's not related, you are not paying per hour, you are paying per the number of data you have processed. But this is not everything. It turns out that Microsoft also integrated Spark engine. So you can see Apache Spark integrated there. So imagine that now you have 3 engines inside Spark Analytics. You can build a regular data warehouse on a dedicated pool. You have on-demand analytics, and you have Spark engine, which is like a Spark cluster, you know it from Databricks. So now you can think about that, okay, maybe I don't need the Databricks anymore. But if you have it already and you perform a lot of analytics there, you should keep it. But for new solutions, maybe you have a choice. And of course, you have also pipelines. So then you can think, okay, if I have pipelines, so maybe I don't need Azure Data Factory anymore because I have pipelines, which are also integrated in Synapse Analytics. And of course, there is a tool which is called Synapse Studio, in which you build everything and you put everything together like puzzles. Now let's talk about the demo that I have prepared for you today. And the demo will be done on the real data. The data I found on University of California in Davis, nearby Sacramento. And what they did is that on one of the highway, which is called Interstate 80, they put like 50 something, 57, 58 so-called measurement gates. So the idea is that the gate was measuring how many cars go through the gate every minute, and also measure the speed. But it was not because they want to, they want to call the police if you just drive too fast. The idea was that they wanted to have information how much this highway is loaded. Because it was a plan to perform some kind of, rebuilding of the highway. So they wanted to know whether it is, when this should be done. And I have, of course, you can, from the University of Davis, from their webpage, you can download data from all the measurement station. I have information from 5 of them, but it's a lot of data. So I downloaded the data to Azure Storage. The data is in Parquet format, so it's already prepared to be in a columnar format. So the columnar format is the preferred format if you do a lot of analytics, because in such case you can apply this directly to, for example, to Spark engine without the need of transformation. And of course, this serverless pool also works the best in the if you have data already in the Parquet format. If you think about, okay, if I have data in CSV file, what should I do? Then just do simple transformation. The simple transformation you can do in Azure Data Factory. You just take data in CSV, save the data in Parquet. It's just in one step. It's very simple task. So it's like a pre-processing that should be done before you really go to the Synapse. So that's this one. This could be this step, for example, here, right? So you just need to, the transformation means that you just change the file format. Okay, so first of all, I have already created Synapse. So let me go to this one. So, creating a Synapse is a pretty easy task, because you just need to go to the cloud and type Synapse and create Azure Synapse Analytics, which is like one step, task to do. So it takes like a few moments to complete, but it's very easy task to create. I have created it before, so I'm going to use the Synapse that I have now, as I have created previously. And I have one more thing here. This is the storage that I have mentioned. So I have a storage, data lake storage for different demos, but I have my storage, which is called Flow. And inside the Flow, I have data from 5 stations. So this is the initial state we have. The data is in the Parquet format, and as you see, it's a lot of the data from each of the station. So each of the station has a bunch of files, and I'm going to read all the files immediately inside the inside the Synapse. So from the Synapse perspective, once the service is up and running, what you can take a look is, first of all, that you have this serverless pool. But the serverless pool, you cannot do much with this because the serverless pool is always available. But as I have mentioned, you cannot control it. So you do not have the predictive performance on it, but you can do a lot of on-demand tasks. If you wish, you can create the regular, the dedicated Synapse pool, and then you can decide how big the pool should be. But you know, the case is here that there is, as of now, there is no automatic, like auto-inflate or deflate the pool as you have, for example, the capability in Azure SQL database, where when you have a serverless model, you can decide the parameters. This is not serverless model, so you cannot do this. You can make it using scripts. So, for example, PowerShell script can help you here because you can imagine that, okay, if I do a lot of data loading and data processing, I would need to have more resources there. But later, once the data warehouse is up and running, and maybe the analytics is also up and running, you can set the resources to some kind of lower level. But this must be your action. So you can create pretty easy and pretty quickly an additional pool. Same story will be for Apache Spark. So as of now, when you install this service, so I mean Synapse Analytics, you do not have any Apache Spark pool because it looks like that, its entire compute cluster. So in this cluster, you can decide how big the cluster should be. So for example, you can decide, I would like to have the minimum 3 nodes and the maximum is 200 compute nodes. Each of the node is this size. So take a look how big cluster you can build. This is the price you need to pay. And of course, you can decide what kind of cluster you would like to build. Hardware accelerated, I would say this is for calculations like you have a neural network, you would like to train a neural network model, for example, for image recognition or something like this, which requires a lot of computational power. In that case, of course, the nodes can be even bigger. Imagine GPU, 64 core, each node, 0.5 terabyte of data, of RAM, of memory, and you have 200 nodes like this. And you can run your code on such big cluster if you need it. So that's a very similar configuration to what you see actually on the Databricks. But I'm not going to create this cluster. I'm going to use today only what you have built in. I will be using all the calculations on the built-in serverless pool inside my Azure Synapse. So if I would like to start my journey with the data, I would have to go to Synapse Studio. So I have already opened the Synapse Studio, and it looks like this in the first place. So first of all, that's the visual place and the visual interface in which you can do everything what you need, including also management of the data connection. So you can imagine that you can, for example, you can create a link service. So that's like a connection to a different data source. And there are like, I think, 50, 60 or even more ready-to-use data connectors. So you can connect to many different data sources. And once you create this connection, then you can just connect and read the data using regular SQL command. Of course, from this perspective, you can also control, so to create a new SQL pools or create Apache Spark pool, whatever you need. And also administrative tasks like access control and credential. This is the part when you can build pipelines. So you can build a new pipeline and you can say, I would like to copy data, right? So what is the source? What will be the location? So the source could be, for example, connection to the CSV file, and the sink, I mean the destination, would be the Parquet file. So this is how you can do the transformation that I have mentioned earlier. So it's pretty basic thing here. But what I would like really to do is to show you how I started my analytics on the data that I have from the University of Davis. So first of all, what I have created is I have created a view. If you have ever worked with databases, then you know that most of the time, unless you create an index view, then a view does not hold any data. So it's like only a definition. It's like a query definition, which is stored as a view. And take a look. In my view, what I do is I'm connecting using open row set function to my data lake, to this measurement station, and I pick all Parquet files. Then I do, of course, there is also, a condition that when particular column is greater than 0, and I will explain you what the column is. You will see it in a moment. And take a look. I do it. I'm performing select. I do union all. I'm taking data from another station and another station and another station. But this is, creating a view is not running a query at all. It's just like a definition. So I'm creating the definition and it says, no, something is wrong here. Object is in the database. I should have started drop view if exist. That should be my first statement. So let's do it one more time. So query executed successfully. And then what I would like to do, I would like to take a look, what do I have in my data? Because I'm starting exploration of the data. And in a moment, I would like to show you how can we perform a little bit of data science using only pure SQL without doing anything in Python or Scala or any other languages, mostly Python, of course. So let me do top 10, select top 10 from view. And now it's the moment when the data is really accessed. So imagine that there is a storage and I'm performing select top 10. So I don't know what 10, what kind of rows do I have. It will be just first 10 that is accessible. So now I have information what is inside the files. So you see, this is the data is about the road, right? About highway. So we have information that for every lane on the road, we can measure how many cars there were. What is the occupancy in percent? So this is like 3% of occupancy. This is 8% of occupancy of the lane, and the speed, the average speed of those 6 cars. And as you see, we have 2, we have 3, up to 8 lanes. And this is the measurement station name. But as you see, we have a bunch of nulls, right? And only 3 lanes are actually sending some data. And the lane starting from lane number 4 up to lane number 8, they do not have any data at all. So you may ask a question, is it an error in the data? So something is wrong with the data, or this is the desired result? How to check it? You see, now we do the analysis, right? This is data exploration. So what should we do? So my idea was to open Google Maps and go there, and I will check what was the name of the nearby village. It was called El Macero. Oh, this is here. Let's make it a little bit smaller. Oh, that's the highway. That's the highway. And you see we have data from, so that's the University of Davis, and that's the highway Interstate 80 with those 50-something measurement gates. So how do I check whether, why do I have only data from 3 lanes and not from 8? So I did something like this. I put the guy here, and I try to let me go to this, highway here. And you see, that's really true that we have only data from 3 lanes because there are only 3 there. So lane number 4 up to 8, they do not contain any data because there are only 3 lanes on the road. So that's really a good result. So I don't have any initial error in my data, which is fine. The next step, what I would do is I would go and take a look, what is the data distribution? And this is pretty easy SQL query, right? For each station, measurement station, I would like to count how many rows do I have from each of the station. I am performing group by grouping set operation. So now I'm aggregating data across all the stations that I have. So now you can imagine that I have millions of files and I'm trying to read information from them. It should be like in a few seconds. So take a look. So I have data from each of the station. Those are the number of rows, and this is the total number of rows that I have. So 1.3 million of samples, data samples. And then I started one more query. I hope I have the result already there. You know, this is the type of query which we usually don't run because, you know, when you perform analytics, analytics means that you are doing some kind of summarization, statistical view on your data. So the statistical view means that you are not doing select star or select columns from, right? So this is not analytical query. As it is not analytical query, it took 90 seconds. So, you know, I don't want to you to wait 90 seconds for the result. So I started the query prior to our meeting. Now I have results. And you know, the reason I like the Synapse Studio very much is that I can view my data in a tabular format, which is one thing, but I also can see the data in some kind of visualization. So I can imagine what really happens. So I try to configure the chart. Let me put time on the x-axis here. And on the y-axis, I will show you what we can see. So first of all, we will see the flow of the cars. So you see that there is moment when there are like 20 cars during the day. Then if there is late night, like 1 a.m. in the morning, we have only 4 cars. And then we have again during the day many cars, and at night we have again the road is almost empty. That's flow 1, which means you are on the lane number 1, which is in Europe and United States, is on the right hand side. It should be the most frequently used lane. Then you have a flow on the lane number 2 and flow on the lane number 3, which means that, you know, the third lane is only usually for the cars if you try to if there is no place on the first 2, right? So this should be the least usable lane. And as you see, it's like this. We can also compare the speed. So what is the speed on the first lane? What is the speed on the second lane? And what is the speed on the third lane? And you see it's almost the same, right? So it's fine. So the car are moving just in the parallel, like in the parallel. But then you may ask a question to yourself. Maybe there are some, some dependencies, right? So maybe I can find a dependency between the flow and the speed. Maybe there will be a dependency. Maybe, on this chart, we cannot see it very well, but, during the day, you have the speed is a little bit less. Take a look, 70. And at night, people are, sometimes you see 80 something and more. So maybe we can create a model, the simplest one you can imagine, that can help us analyze the data. And having a data model like this, we can perform a lot more advanced analytics. And that was my goal for this type of data. So first of all, I'd like to tell you where we should go. And then I will explain you the rest of the demos. So let me just, I try to, I think I will be able to draw something for you. You should be able to see my notepad. Sorry, my OneNote. And the idea here is that I would like to create a model of the simplest model you can imagine. It will be a regression model. The simplest one we can have. Where is my? It's my notepad here. I'm trying to find the when I. Okay. Now I see where am I on the page here. Okay, so now I can draw all the necessary things. So my idea was to create a model which will be like this. I would like to create a linear regression, and linear regression is the simplest model that can be understand. It looks like this. So you have an output, and the output is a linear. It's a function in linear function of the input, and we can have data in a format like this. So imagine that we have this x-axis here, we have the y-axis here, and we have a bunch of points, measurement points taken from the measurement station. And now the question is, what type of function should I pick? Because, you can imagine that one of the functions that you could pick could be something like this. But, this is not type of function we can see in the real life because it's too complicated. So you can think about this function, this red one, as the function that only works or will work with this particular data set, number of points. This function will not work in general case. You should always start with something simple. It should not be too simple, but it should be simple enough to describe the reality. So we can say that we'd like to find a function that looks like this, right? But then you can ask me, hey, and what about another function? Maybe a function, this one is better. Or maybe we have another function, and maybe this one is better. Which one fits the best? That's the question here, and that's the question that we have to answer using our SQL statement in Synapse. And if you ask me, hey, where those functions are, do we really need that? Think about simplest transformation of the temperature. So if we have a Fahrenheit temperature, you know that this is a very simple calculations like this, right? So that's the transformation we do for the calculations between Celsius and Fahrenheit. I will change it a little bit because I'd like to put it in the form of the coefficients that I have below. So take a look. This is this is something that I'm going to predict. This is the prediction, right? This is the coefficient which is called A. And what is the physical meaning of it? This is the 32. This is a temperature. So anytime you do a linear regression, so the coefficient which is called A has to have the same meaning like the output. So it has to be in the same dimension, which means that if the output is a temperature, that also A has to be a temperature. And then you have a scaling component, which is this one. And this is the second coefficient that you can control to choose the proper line. So depending on A and B, you can choose line 1, 2, or 3, or maybe some other lines as well. So I will show you in a moment a general expression how to calculate A and B, because those calculations I use in my demo. But first of all, we need to decide which line we'd like to pick. And in general case, what we'd like to achieve is to have a line which fits the best. What does it mean? And I will now draw, a simple case. It will be very simple, but I hope you understand what do I mean here. So first of all, where are the coefficients? So A and B, where can we find them? So the coefficient A, and if you take a look here, so the coefficient A will be visible in a situation, in our case, when C is equal to 0. So then the temperature should be 32. So this is actually the A coefficient. So it's called, if you go to a literature, go to the books, this is so-called interception. And then you have a coefficient B, and it looks like that B is somehow related to this angle we have here. So the bigger the B is, if the B is bigger, then the angle is also bigger. So you see, it looks like this. So the more B you have, the bigger the angle is. So this is what we this is how we understand those coefficients. And the definition of the best line is a line that minimizes the error between the point that was that is predicted, so we can call it like this, and the point we have really here. So in each place of the line, we can find a point that we have. That's the point we have from measurements, and that's the prediction. So what we would like to do is we would like to minimize the difference between those points. And in the first glance, you can think about, okay, let's minimize a difference like this. So I would like to keep on minimum level something expression like you see on the screen. But then you may think that if this error has a plus sign and this error has minus sign, so if you just calculate the expression like y predicted minus y actual, this is y actual. So then having a situation like this, you might end up with error which is equal to 0, which is not true because you have an error. That's why what we typically do is we try to square it. And then the case here is to minimize so-called a function, which is called cost function, which is sometimes called Q. And the cost function is to minimize the error, which is described like this, that we'd like to perform a summation of the differences between the predicted value minus the actual value in each of the point we have, right, squared, and then of course we can perform a square root from it to perform a very familiar calculation. So that's a little bit of math, but now I will just tell you a little bit, and this will be, I promise, this will be the last math you see, but you have to know it because then I show you how I implemented it in SQL. So the A coefficient will look like this. So let me scroll here. So you see the A coefficient. It will be the sum of the Y multiplied by the sum of X squared minus sum of X, sum of XY divided by the number of samples you have, sum of X squared minus sum of x's, and the B coefficient will be very similar. It will be sum of xy minus sum of x, sum of y, and here we have the squares minus but it's a little bit, it's y here, not x, it's y here squared. And there is also R coefficient, which tell you how good the line fits to the points. And if you think that I am smart enough to remember this A and B coefficients, that you are wrong. I just went to the web page which has all the coefficients described, and I put the numbers here. And the reason is only one, because I would like to show you my actual implementation. So I have 10 minutes and it's just the right time to finish the demo. So first of all, before I go to the statistics, I would like to show you the remaining part of the analytics that I have done on my Synapse. So first of all, I wanted to see how much my lane number 1 is occupied on each of the station. And the result I'm expecting is like between 0 and 1. This is something that we should see on each of the stations. So you see it's mostly true. So we have 0 and 95%, 91. But on the station number 62, you see that's only 39%. And it looks that there were some road works. So it was not possible to use all the lanes and have the occupation close to 100%. I have created one more view, and the view was defined like that I wanted to have all the possible statistical functions that SQL Server exposes. So take a look. I have minimum, maximum on occupancy, flow, and speed. And then I wanted also to have average. And I wanted to have standard deviation, right? Because if I have only average, then it's not possible to get some meaningful results. And now we have this coefficients that I draw for you on the on my notepad. This sum of y, it's described like so that's the sum of y. You see it here. Sum of x square, it's this one, right? So you can refer to this notes if you wish later. So this is how I created those coefficients, and those are real data. And first of all, I started to have it from one station to make sure that I can understand what's going on. I created all the necessary sums, and I created the my first approach here to make sure that I understand how the coefficients looks like. And take a look, that was my first result, but you have to first ask the question, what am I analyzing, right? So I'm analyzing flow on the first lane, how the flow on the second lane, so that's my Y, so that's the prediction. So what is the predicted flow on the second lane if I know everything from about lane number 1? And those are the coefficients. So you see, we have a coefficient. A, which says that you have to multiply. That's the interception. So and then you have to multiply the number of cars on the lane 1 and add this one, multiply it by 0.61. So you can say that that's very closely, you can say that on the lane number 2, you have around 60% of cars from lane number 1. This is what is the meaning here, +2, right? So if you have, for example, 18 cars on lane number 1, then 10% is 1.86 times 6. So it will be half of them. It will be 9 plus 1.8. It will be 10, 13, 14. 14 cars will be on lane number 2 with probability 84%. So this is how we can read it. But then I created also a view which I'm going to show you now, because I was very curious about a view in which I can say something about the speed. So if there is a correlation, linear correlation between the speed, between the flow, how many cars do I have, and also the speed. So the speed is something that I would like to predict basing on the flow that I have on the lane number 1. So I have created a view that explains this situation, and I would like to run the final query for you just in a second. So let me show you this one. And we should have the answer pretty quickly from all the stations. Information that, take a look. We have the A coefficient, and I have told you that the A coefficient has to be in the same dimension, so it has to be the same physical representation than the value you predict. So in my case, as I am predicting the speed depending on the flow, so that's the initial speed you have. So on the lane number 1, you have 78 miles per hour, which is kind of big one. And then the coefficient B has minus sign here. What does it mean? That means that my line is not turned, it looks like, I will show you this quickly, which means that I have data like this. So I have 78 miles per hour, but the B coefficient is less than 0, which means that, and this is the flow. So I have some kind of numbers. If it is less than 0, which means that if I have more cars on the lane number 1, the speed has to be smaller. So this is something that we can also imagine that it should work this way. And I have this information also from the data. And to conclude my session, think about it this way. I have a question from business, which they want to know, how should we interpret the data? We have a lot of data, but we don't want to build the entire system around this. First, we'd like to perform some kind of analytics on the fly without investing too much into infrastructure, just taking the service, but not investing, in building the data warehouse and analytics. I just use a SQL Server capabilities and SQL queries on data which are stored in the files, and I have them in the data lake. And I use the regular SQL statement to create a linear regression model against the data. So if I'm happy with the model, I can perform a lot more advanced analytics. But I started with something very simple, and this is why I think Synapse will be the perfect solution for you if you would like to start your journey with playing around your data. And having said this, I would like to conclude my demo. I would like to thank you very much for having me here in this excellent event. I'm very happy to be here with you.